The second thing to consider is novelty and diversity when generated from an engineering perspective. To begin with, there are several critical issues that we really need to think about when utilizing these complex generative models from a practical engineering design perspective. For example, while we can certainly verify the overall performance through detailed simulations, the actual computational cost involved is simply just too high for most projects. And it's even more difficult to evaluate in the real world. It's harder to test. And secondly, there's the problem of data sparsity. In the field of engineering, the dataset we have cannot represent the entire design space uniformly. For example, if the entire design space looks like this, the data we have is likely to be concentrated in a specific area. We find ourselves unable to fully explain this specific part, and as a result, a certain level of sparsity exists within these areas. Furthermore, there is a noticeable gap that arises when it comes to the concept of true creativity. From a mathematical perspective, the designs we generate might technically be considered new. But in reality, there can be a very significant gap between those results and what the customer actually desires as something truly innovative. And finally, we must also consider the critical factors of practical usability and technical feasibility. This is also a significant issue. In the case of 3D designs generated by AI, they may not include parametric details. For example, if it just generates a mesh form, then people can't make any modifications to it. So, in the case of typical CAD models, they are parametric and have a history, which allows people to make modifications based on that. But when it comes to AI-generated models, it's difficult for people to make direct modifications in that way. Therefore, some research into converting these into drawings is needed. Looking at it in more detail, if you want to increase the novelty and diversity of the designs you generate, you first need to be able to define what novelty and diversity mean. For example, in the case of design novelty, you need to compare how unique a design is compared to existing designs, and there are various ways to do this. For example, in the first method, if the generated designs are green and my dataset is gray, you simply calculate the distance to the nearest neighbor for each generated design and sum them up. The larger this value, the higher the novelty. In the second method, you calculate the distance from each generated design to the closest actual ground truth data point and sum all these distances. The greater this total distance, the higher the novelty is considered to be. And finally, the third method is to find the center of the generated designs. Then you sum up the distances from this center to each generated data point, and the greater this total distance, the higher the novelty. So what about diversity? There are some similarities. However, when we look specifically at the concept of design diversity, it is really about carefully examining how the overall variety or the broad range of these newly generated designs differs significantly from the collection of existing designs that we already have. For example, the first method involves creating a smallest enclosing hypersphere. So you take the outermost points of the generated data and form a sphere around them to calculate the radius. The larger the radius, the greater the diversity. The second method is to create a convex hull using the outermost designs, and the larger the area of this hull, the more diverse the designs are. Lastly, there's something called pairwise distance, DP, where you calculate the distances between all pairs in a one-to-one matching. The greater these distances, the more spread out the designs are. And that's how diversity increases. So, if you truly want to increase the overall design novelty or the creative diversity of your outputs, even when you are training a traditional GAN model, you can include a specific measure that carefully calculates both diversity and novelty. You then add this metric directly into the loss function and optimize the entire system accordingly. As a direct result of this process, you will end up generating brand new designs that go far beyond the limitations of the original training dataset. This demonstrates that result. And as for diversity, it shouldn't just be examined in terms of design shapes or only in design X. It also needs to be checked from a performance perspective. In the performance space, that is. The reason is, for example, if we randomly select points in the X design space and then run a simulation with those points, the Y values can actually converge to just a few points. That means that while X may appear to be diverse, in reality, y is not actually diverse. So instead of randomly selecting x, let's use the DOE methodology we know to spread them out more broadly and evenly. However, even then, you can see that the y values still end up clustering around certain values. So this approach doesn't work. We can't just consider x alone. We need to calculate y from x, then, based on y, identify the x values that result in different y values. That way, we can collect data that has diversity from both the x perspective and the y perspective. That's the main point I want to convey on this page.